Okay, this is the Introduction to Qualitative Analysis of Cations lab. If you don't have the lab in front of you, please find it. It's on page 99 or so in your lab notebook. This is the first page of the lab. And then there's also a pre-lab exercise that's a couple pages before that. I think it's the pre-lab itself starts on page 99, I think, in your lab notebook. So find that lab and we're going to kind of read along with it. And then after we read along with the introduction to the lab, then we'll talk about what types of things you need to write in your lab notebook. And also we'll do a number of the pre-lab exercises as well. So you're prepared to come in on on Tuesday next week and start the lab. Okay, qualitative analysis is an analytical procedure in which the question, what is present, is answered. In a systematic qualitative analysis scheme, each substance present is separated from other substances. Then a confirmatory test is used to prove that the isolated substance is the expected one. In this experiment, you'll analyze a solution that can contain any combination of 10 different cations. These are the 10 cations that the solution can or will contain. First of all, you'll prepare a solution, or it's already prepared for you actually, that has all 10 of these ions dissolved in it. You'll learn the techniques and analyze all 10 and separate them so you know how to find all 10 of those. Then you'll be given an unknown. Your unknown solution will contain 3 of these 10 ions. You don't know which 3. You'll have to go through the same scheme and determine which 3 are in your unknown solution. Your grade is primarily based on your ability to find your 3 unknown ions. This experiment is carried out on a semi-micro scale. Very small quantities of reagents are used. Cleanliness and a great deal of care are necessary to obtain good results. As you go through the steps of the analysis, keep a copy of the flowchart available for reference. The flowchart appears at the end of the experimental directions. It will help you see the total picture of where you are and where you're heading. Read the directions carefully and read the sections which give the notes or the chemical theory for each step. Don't just follow the directions cookbook style, but make an effort to understand the principles of chemistry behind the procedures. Next section, general techniques for qualitative analysis. Keep good records. It's necessary to keep good records so that you don't get confused and forget what solutions are in which test tubes. Number your test tubes with a pencil or permanent ink so the numbers don't come off in a hot water bath. You should be able to write on the white spots of the test tubes. Maintain a current record of your work. Don't trust your results to memory. In your lab notebook, set up a table that looks like this, where it says step, and then you can number the step 1, 2, 3, etc. Procedure. The results of that. Like, for instance, I got a white precipitate, or I got no precipitate, or it was a blue solution. Conclusion. I conclude that copper is present, or something like that. This is for your known solution right here. This is for the one that has all 10 ions in it. And then you can put a place for your unknown solution right here with results and conclusions. So then you can look back and refer to, hey, I did this for the 10 ion solution. And now my unknown, this worked, this didn't work, this worked, this didn't work, and it will tell me whether or not I have those particular ions in solution. See, these are the test tubes that you'll be using. And you can see that there's a small little white box on there. And if you use a pencil, you can write on there and it won't come off in the hot water bath because sometimes you have to heat it. We'll show you some of the other equipment as we go along as well. Them aren't filled yet because we're not going to fill them until right before the lab starts. But this, for instance, would be the 6 molar H2SO4. 6 molar is fairly concentrated sulfuric acid. It's not something that you want to leave the cap ajar on and leave it sit like this at your lab station. So safety and care is really, really important in this lab. When you pick up a bottle, never pick the bottle up by the cap. because just in case somebody would leave the cap loose, maybe you'll pick it up and boom, over it spills, and now all the solution from there tips onto the table before you put it back on the table. And second of all, just for added safety, always make sure to pick up the bottle by the bottle, not by the cap, just in case somebody forgot to put the top on tight. We have 7 different lab stations in here. Each lab station will have a set of chemicals that people can use. There are a few chemicals that you don't use very much that won't be at every single lab station, but most of them will have a majority of the chemicals that you need. Okay, we're on the second page now on the topic called avoiding contamination. Tap water is often a source of contaminating ions. Wash all glassware and rinse it with distilled water. A stirring rod is constantly used to mix solutions, and it must be rinsed with distilled water so it does not contaminate subsequent solutions. An easy way to do this is to fill a 400 milliliter beaker about 2/3 full of distilled water and keep your stirring rod in this beaker. A small amount of contaminants present in this volume of water should cause no problem. Replace the distilled water if it appears to need it. So just out of your lab station, grab a distilled water and put your stir rod in there all the time. When you use chemical reagents, do not turn the droppers upside down. So for instance, here's a dropper. Squeeze the dropper, get your solution out, and hold it this direction. Don't hold it like this thinking, oh, the solution won't come out, because then the solution goes into the rubber part of the dropper, and then some of the solutions will actually react with that. Now you don't have your solution anymore, you have rubberized solution or whatever it is. So make sure that you just hold them up like this and then do the dropping. Generally, measuring solutions. Generally, you should estimate the volume of the solution that you add. Notice it said estimate. It's not necessary to use a graduated cylinder to measure the solution volumes. You might wish to calibrate a test tube in milliliters just to give yourself an idea of what a volume of a milliliter actually is. You may also want to count the number of drops in a milliliter. The general rule of thumb for these droppers is 20 drops is about a milliliter. But they usually just tell you to add 2 or 3 drops. And since the name of this lab is called qualitative analysis, not quantitative analysis, what you really want to know is what is actually in the solution, not how much is in the solution. Heating solutions. Frequently it will be necessary to heat a solution to speed up the reaction. Do not heat small test tubes over Bunsen burner flames. As a matter of fact, we'll only have hot plates at the different stations, and one of the first things you should do when you get here Tuesday morning is to fill up your beaker of distilled water, put it on your hot plate, a fairly large beaker, maybe about a 600 or maybe a liter beaker, and turn it on and get your water heating and boiling. I suggest using distilled water because then it doesn't leave scale on the inside of your glassware. And we only use a hot plate too, because then you don't have flames around either. With your test tubes, when you heat them, then you'll put it into a test tube holder, and then you just put that test tube into your hot water bath. Stirring solutions. Each time a reagent is added to a test tube, now each one of these little bottles right here is called a reagent. So the sulfuric acid is a reagent, the KSCN would be a particular reagent for some step. Each time you add it, it needs to be stirred. It's important to mix the solutions at the top and the bottom. A stirring rod sometimes helps with this. So take your stir rod, dump it in there, kind of swirl it up and down. Separating solids from solutions. We use what's called a centrifuge to separate the solids from the solutions. This is a centrifuge. We'll have 5 or 6 of these throughout the lab. Notice they have a little top to them, and then they have a little spot right down in here where you can take test tubes and just slide them into the holder. Okay. When you use a centrifuge, it spins the solutions around really fast inside of it. And what it does is it takes the solid that might be dissolved in the solution and compacts it and brings it down to the bottom of the test tube. When you load a centrifuge, it's really important that the centrifuge is balanced. If the spinning part of the centrifuge is unbalanced, then it'll start to wobble and sometimes, in some cases, actually start to kind of walk across the table. And of course, that's not a very safe situation. And so when you load a centrifuge, make sure that you put your solution that you want to centrifuge on one side, and then add another solution, or a blank test tube with some water in it, exactly opposite of it. Exactly opposite. And if you look at the bottom of your page that we're looking at right now, it says page 124 on mine. You can see how to safely load a centrifuge. And if you want to centrifuge more than 2 things, this can hold up to 8, you could partner with somebody next to you and put their solution opposite. Or some people like to run 2 or 3 trials at the same time. And maybe you want to have the other people put theirs opposite of yours and see how they go. One goes this direction, one goes opposite, and they just have to be all equalized out throughout the centrifuge. So if you're going to centrifuge 3 things, you can do that. Just make sure that they're at 120-degree angles to each other. When you do run the centrifuge, there's a couple controls on here to show you how to operate it. This is the speed control right here, and then this is the timer. The timer actually makes a ticking noise if you listen really carefully. And then when it's done, it makes a neat ding. But to make the centrifuge run, you have to engage the cover. It won't run without the cover attached. And this part of the cover right here is actually a conductor of the electricity that runs through and makes it spin around. So if it doesn't work sometime when you're closing it, you probably know that maybe this needs a little filing down, or it's just not conducting real well. So close, once you load the centrifuge properly, close the top of the centrifuge, and then you turn the knob and make sure that it engages properly with the inside of the centrifuge. Then you can turn it on, and generally you want to centrifuge for 2 to 3 minutes. Sometimes people do it for longer than that. Make sure that the test tubes stop moving before you open the centrifuge. People, after one day, usually are quite impatient. They'll open the top of the centrifuge, and then they'll start to poke their finger in there to slow the centrifuge down sooner. First of all, it's not real safe, because what happens if you catch your finger on one of the test tubes? Second of all, it might not allow your solution or your solid to settle out quite as nice as it should, and so then all the centrifuging that you did to get your precipitate to the bottom of your test tube is kind of wasted. So it's best just to find something else to do for a little bit, and that's why some people run 2 sequences of the solution at the same time. They'll centrifuge one, and then they'll go read and do the reaction for the next part while it's centrifuging. Then when it's done, then they'll swap, and they'll take one test tube out and put another one in. Okay, that's centrifuging. The next page, it says on mine 125, washing precipitates. It's almost always necessary to wash precipitates to free them from ions, which might cause confusion later in the steps. To do this, add 1 to 2 milliliters of distilled water to the precipitate, stir it again, centrifuge it, and discard the wash water. Sometimes the directions will tell you to include a specific reagent in the wash water. There'll be lots of bottles of distilled water around here, and people really like to have their squirt bottle filled all the time. And some people get really particular about where their stuff is. So if you're in an hour, you realize that people the next hour will be using the same equipment and put it back where you found it. Checking the pH. To check the pH of the solution, put a piece of, it says litmus paper, we have pH paper, onto a clean glass plate or a watch glass. Dip your stirring rod into your test tube, then take your stir rod out and touch it to the litmus paper, or in our case, the pH paper. Don't dip the test paper into the test tube. You'll contaminate your solution. So make sure to put the test paper down here, dip your stir rod in, and then touch the test paper. Storing solutions. If you wish to keep a solution until the next lab period, make sure to stopper the test tube with a cork stopper. and then make sure to label it really, really well, because remember there's other people doing labs in here too, and then you can set that aside in your lab station. Don't trust your memory, write it down. Disposal of the solutions. Many of the solutions and ions being tested are poisonous, and so in the fume hood over here we'll have a really large container that says waste solution, so don't dump any of that stuff down the drain. Just go over to the fume hood and dump everything in there. Okay, if you turn the page, you can see that the lab actually starts on page 126 and 127, and they give you a step 1, 2, and if you turn the page, there's a step 3, 4, 5, and you can turn pages for many, many pages in here to actually find that there's at least 15 or so steps, and each step involves some different reactions. And then there's a number of discussion questions at the end. I'd like you to turn, in my book it says page 135, so the page looks like this. It says Qualitative Analysis of Cations Flow Chart. If you take a look at the flow chart, you can see that it actually gives you an overview of all the reactions that you'll be doing. It starts right here with your 10 ion solution at the top, and then you see to that you add some HCl. It should precipitate your silver, mercury, and lead. Hey, that's some solubility rules we had learned. And then the other things should stay soluble: manganese, cobalt, iron, bismuth, copper, aluminum, and zinc. And that goes on to the next page. Then you take these 3 insoluble things, and there's ways to separate those as well. And it leads you through the steps to confirm that those 3 ions are in there. If you turn the page, you can see the schematic flow chart for the other 7 ions. And you see to that, you add some sodium hydroxide and some hydrogen peroxide. This allows our aluminum and zinc to stay soluble as some Lewis acid complexes. Notice the cool complex ions that form. And then over here you can see that a number of things precipitate, and there's a way to separate those out as well. Okay, if you go back to the very beginning of the lab, there's a number of questions. It's called the preliminary lab assignment. It looks kind of like this. And there's a number of questions to answer at the very beginning about the qualitative analysis scheme. We're going to go through a few of those right now, and I think we'll take 10 minutes and see how far we get. And we won't answer every question, but we'll get a good idea of how the scheme works before the lab actually starts. So preliminary lab assignment. On mine it says page 137. Yours it's page 99, is that right? Page 99. So question number 1 says, use the flow chart at the end of the experimental procedure to answer the following questions. In each question, a test is carried out to determine the presence or absence of several ions. Only those listed may be present. State if the test indicates if each ion is present, absent, or undetermined. So in your actual lab notebook, now you can write pre-lab assignment, and you can write number 1, and we'll just do a few of these in your lab notebook, or if you want to do them on a separate piece of paper and add them to your lab notebook, that's fine too. So number 1 says a test for silver, mercury, and lead. Some 6 molar HCl is added to a solution which may contain the 3 ions. A white precipitate forms. All of the precipitate dissolves in hot water. Which ions are present, which are absent, and which are undetermined? Well, to find this, turn to your flow chart at the very beginning and find where silver, mercury, and lead are. Once you find silver, mercury, and lead, look down here, and where does it say something will dissolve in hot water? Well, the next step says hot H2O. Look what forms an ion. Look, lead chloride dissolves in hot water, whereas silver chloride and mercury chloride, they stay as solids. So if it says a white precipitate forms and all of it dissolves in hot water, first of all you added some hydrochloric acid, and since a precipitate forms, silver or mercury or lead must be present, right? Because those will form a precipitate. But then it dissolves in hot water. Which is the only one that dissolves in hot water? Must be lead, right? So ions that are present, lead must be present. What about silver and mercury? Would those be present? Since it all dissolved in hot water, they couldn't be there, right? Because they would have stayed as a precipitate. So the ions that are absent are silver and mercury. Ions undetermined, you can say none of them are. So you can see how this lab is made to actually teach you some other chemistry that you might not know. That, hey, lead chloride, usually a precipitate, will actually dissolve in hot water. A good way to separate it from silver chloride or mercury chloride. Okay, question number 2. A test for silver and mercury. A white precipitate, which may be silver and or mercury chloride, is treated with 6 molar ammonia. A black precipitate forms. Ions present, ions absent, ions undetermined. Well, if you look at your little schematic diagram, and you look at where there's mercury chloride and silver chloride right here, if you add ammonia to it, which one forms a solid? And which one dissolves? Notice silver forms a complex ion with ammonia, and it dissolves. So if you look back at the question, it says, a black precipitate forms. Well, when you add ammonia, you know that if there was silver in there, it would have dissolved. And if you read a little bit further back in the book, I think it's procedure number 3 or procedure number 4, it'll actually tell you in there that the black precipitate is the mercury compound. So ions present would be mercury for sure. But when we added that, does it tell us if there's silver in there or not? It doesn't tell us for sure, does it? We'd have to do a confirmatory test with the liquid, with the solution, to find out if silver's there. So we have to say that silver is undetermined in number 2. Okay, let's do one more. Number 3 says, test for manganese, cobalt, iron, bismuth, and zinc. A colorless solution is known to contain one or more of the above ions. Some 3% H2O2 and NaOH are added to the solution and heated for several minutes. A white precipitate forms. Which ions are present, which are absent, which are undetermined. So now if you find the manganese, cobalt, iron, bismuth, and zinc on the second page, and you can see that they added some H2O2 to it right here, and some NaOH to it. Which things precipitate? Which things stay as a solution? Well, it says that it's a colorless solution, and that's a clue. And I'll have all 10 solutions out here for you to see before you start. And it turns out that cobalt, manganese, and iron actually have some color to them. And you should memorize those colors like we've done in the past. The second thing is that when you add a NaOH and H2O2 to them, which one of those ions that's in there will actually dissolve? Now we ruled out manganese, we ruled out cobalt, we ruled out iron. What about bismuth or zinc? Will one of those dissolve when you add H2O2 and NaOH? Look at your flow chart. Yeah, if you look to the right-hand side of your flow chart, zinc OH4 2- will form. So zinc would dissolve when you add that. So what must be the only thing that could have made a precipitate there? It must have been the bismuth. So ions present would be bismuth. Ions absent would be the colorful ones, manganese, cobalt, and iron. And the undetermined one must be zinc, because it would have dissolved. Okay, the rest of the problems, 4, 5, 6, 7, and 8, and then there's some on the next page too. I'd like you to try the next couple of them and see how you do, 4, 5, and 6 at least, on your own. Just see if you can answer those questions by looking at the flow chart, reading through the lab, and becoming familiar with the equipment and with the techniques. So then when you walk in on Tuesday or when you walk in next week to start the lab, then you're prepared to come back and start with the 10-ion solution, the solution that has all the qualitative analysis ions in it. And you can start from step 1, take good notes as you go along, and separate the ions. So then when later in the week it's time to start with your unknown solution, you've got a good reference to look back on.